Hi, I'm Chris Broadfoot. I work on the Google Maps API.
And I'm Andrew Gerrand, and I work on the Go programming language. And today we're here from Google in Sydney to demonstrate a HTML5 Google Maps-based web app that uses the Go runtime on App Engine to perform some intensive computation in the cloud. And before we get into the guts of the app, I'm going to get Chris to talk about the problem that our app tries to solve.
Cool. So this might look familiar to you. It's a map of the world of satellite imagery taken from space. This here is also taken from space, and it's a cloud layer. So this is available through the Maps app and also through the Maps API. Late last year, Google Maps Mobile added indoor floor plans to the base Google Map. So essentially, they overlaid quite detailed indoor information in context with the sort of map of the world. Loughborough University has done a similar thing by adding custom imagery on top of the base Google Maps so that their visitors can navigate from the world and also within the campus. And so this is a Maps API application. So what you're seeing here is kite imagery taken by Frank Taylor on his Tahina expedition. So I think this is in French Polynesia somewhere. So he's flown a kite up and taken some aerial imagery. And so you can see sort of a little clearly where his really high resolution imagery has been meshed with the lower resolution Google satellite imagery. And so if I zoom in all the way, you can see how detailed this is. I think this is zoom level 22 or so. And you can see these two guys riding their bike, someone standing there, and a car. So consider maybe yesterday you jumped out of a blimp, you were wearing Google Glass, and you took some really awesome imagery. You'd want to get this onto a map somehow, right? Show it in context with the Google satellite imagery. You can do this with the ground overlay class in the Maps API. You essentially tell us where the imagery is and pass in a lat-long bounds, so a region on the Earth, essentially a rectangle, and you end up with something like this. There's a trade-off between size and high resolution. In this overlay, we're sending the whole image down to the client. So you'd either have to send a large image to get really high detail when you zoom in, or suffer low resolution imagery once you zoom in. This is the same problem that we have on Google Maps. So consider that the width of the world at a particular zoom level is 2 to the power of that zoom level times 256 pixels. So at zoom level 21, that's 536 million pixels. And that turns out to be 288 quadrillion pixels if you have really high resolution imagery at worldwide coverage. So that turns out to be 40 petabytes, which is completely unreasonable to send down to a browser. Even if you could send it, they wouldn't be able to render it, right? So the way Google Maps solves this is by using tiles. So at zoom level 0 at the top, the entire world is represented by one tile. And as you get further and further zoomed in, more and more tiles are used to represent high resolution imagery of the world. So at zoom level 21, there's many, many tiles, right? So this same tile-based approach can be used for map overlays. If you've used the map in the I/O Android app, this uses the same tile-based approach. And indeed, we generated these tiles using the app that Andrew and I will demonstrate today. So if you zoom in, you get a really high-resolution, sharp image that matches the base Google Map tiles. So it's really easy to add this tile overlay. You create an image map type, you tell the Maps API where to find the tile image for a particular coordinate, and then you add it to the overlay map types. Now, the I/O Android map has about 1,000 tiles for that small area, and you can imagine that generating these tiles is a little difficult. So we have some really great tools that these two are open source, and they help you generate these tile overlays. So the first one, GDAL. GDAL Translate essentially encodes some location information into the image. So we can see here we're converting between pixel coordinates and positions on the Earth. And then we can use GDAL to tiles or the map tiler project to generate a tile, sort of a tile pyramid. Now these tools are really great, but as I demonstrated at I/O last year, it's quite difficult to find those precise coordinates. So I demonstrated an application last year that helps you with this, but this year we've got a more complete solution. So we've open sourced it. It's called Overlay Tiler, and you can download the source code here. But today, Andrew and I will be showing you some of the details about how we built it. So let's jump straight into a quick demo. So today we'll be adding the Moscone floor plan. So this is essentially what I did a few weeks ago to generate the floor plan for the Android app. So this is a floor plan that we got from our vendor who did all the fit out. And so if I go and search for Howard Street, zoom straight in. And then I'm just going to drag the image from my desktop onto the map. And once I drop it, you'll see that the image is added exactly where I dropped it. And I get these 3 control points that I can use to drag the image around the map. I can also use this one in the middle to just translate it around. And I can precisely and directly manipulate the image on the map to see what it'll look like. So I can also use this opacity slider just to make sure it lines up with the base Google Map tiles. Or perhaps if I'm going to eventually put it in satellite mode, you can see it's slightly offset, so I might actually move it there. And then hit the process button. And from here, the overlay is uploaded along with its coordinates to App Engine, where App Engine will go and generate a tile set. And once that's done, I'll download a zip file, and all the tiles will be in that zip file along with a implementation that adds this overlay to the map. So if I go ahead and unzip that, and open up index.html. Oh, so let's have a look inside here at some tiles. So these are the tile coordinates. So I can see, part of the Moscone Center. If I open up index, we see that the overlay is added to the map, and we can zoom all the way in and get high resolution tiles. Okay, so we'll be showing you some of the details about how we built it. Just quickly, we used HTML5, the Maps API, and Go and Google on App Engine. So first of all, I'll start with the user interface. So the first thing you'll notice is that the page is filled with a map. If you have a mapping-based application or an application that's sort of quite map-heavy, you should go ahead and fill the page with a map. Nothing hurts me more than to see a map-intensive application that has a really tiny map. It's a horrible user experience. So the other thing is, if you're giving your users a way to navigate around the world, add places autocomplete. It's really simple. It's about 3 lines of code, and your users will love you for it. So once the user's landed on the page and navigated, we drag and drop the image to the map. So we do this by listening to the drop event on the map element. You can use any element on the page. And from there, we get a handle to the file on the local file system. So this is something that traditionally browsers haven't offered access to. So this is a really great way to perform client-side manipulations. You don't need to send this file to the server to begin using it straight away. So we create an object URL, which gives us a URL to the local file system, and create a new overlay at the X and Y coordinates that the user dropped the image. So to add the overlay to the map, we use a Google Maps overlay view. So this is a class that you implement these 3 methods, onAdd, draw, and onRemove. So draw essentially is called when the overlay should be re-rendered. And getMap and getPanes and getProjection are really useful to render the overlay. So once the image is added to the map, we create an image element. We set the source to the URL on the local file system, and we add it to the overlay image pane. You see at the bottom we're calling get panes. And this is a handle to some of the map panes so that when the map is panned, your overlay is translated with the map. So once the overlay is added to the map, you need to give the users some way to manipulate it. We do this by adding 3 control points, top left, top right, and bottom right. And for each one, we add a marker. The user is able to drag it around, and we use the bind to function to bind the position of the marker to the control point on that overlay, so that whenever the marker is dragged, the overlay's control points are updated as well. Now, whenever the user drags a marker, whenever the position of those markers change, we need to re-warp the image so that they get a really sort of direct manipulation feel. We do this with an affine transformation. So affine transformations are sort of 4 types of transformations: translation, scaling, rotation, and skew. And so with those 4 transformations combined, we can do something like this. And so this represents all of the operations that you can do based on 3 control points. So using an affine transform, we can warp the image whenever the user drags the marker. We use request animation frame to synchronize the paint events of the browser with our own paint events. And we set the transform property on the image. So down below, you can see the CSS property matrix. And so this is the matrix that represents the transformation based on those 3 control points. Oh, and it's also the exact same matrix that we'll be using on the server side later, and Andrew will talk through that. So when we first created this app, we dragged a large overlay. I think it was tens of megabytes or hundreds of megabytes, and the browser slowed to a crawl. This is because it was just too much work to be able to transform this image many times a second. So when the user drags the image to the map, we check if it's larger than a certain dimension, and if it is, we just resize that image in the browser using Canvas. Using Canvas, we can paint an image to a canvas and turn it into a data URL. And then we update the source of the image, so it's scaled down. While this is all happening, the full-size image is being uploaded to Blob Store on App Engine. So as soon as the user drops it, the image is uploaded, but they're immediately able to manipulate the image because we have access to that local file. So we just upload in the back end, and once the user's finished manipulating, once they press that process button, the 3 coordinates of the control points are sent to the server, and the server starts tiling the image. So Andrew will talk more about what happens now.
Thanks, Chris. So now that we've seen the user interface and how this was constructed, I want to talk about how the tiles are processed on the back end and the zip file is created. So as I mentioned at the beginning of the talk, we're using the Google App Engine platform to build this app. And who here's used App Engine before? Anyone? All right. So of those of you who used it, who's used the Go API before? Ah, that's great. For those of you who don't know, the App Engine platform is Google's platform as a service offering. That is, we take care of all the infrastructure worries, building it out, scaling it, and administering it so that you don't have to, and you and your team can just focus on building scalable, reliable web apps. In this application, we actually use a variety of the services available in App Engine, and I'm going to talk through some of that. So just an overview of how the app works. There are 5 main parts of the app. The first is the upload handler, which receives the file from the user and stores it into the Blob Store service, which is a service for storing large unstructured data. The second is the process handler. And this receives the set of overlay coordinates. That is, when the user has positioned the overlay on the map, it sends the latitude and longitude of the top left, top right, and bottom right corners of that overlay. And the process handler takes those coordinates, it takes the original overlay image, and then computes which tiles need to be generated at what zoom levels, and the coordinates of those tiles, and then creates some tasks which are fed to this next handler, the slice handler. And so the slice handler takes these tile coordinates and the original image, and then performs the transformation that the user requested in the first place using an external package called GraphicsGo, which provides an Affine Transformations primitive, which is very convenient for what we're doing. And then it encodes each of those new tiles as a ping image and stores them into the data store. Once all the slicing is completed, it kicks off another task, the zip task, which collects all of the tiles that have been generated, and then generates the index.html file that we saw earlier, and then bundles all of those files together into a zip and stores it in the blob store. Finally, the user is prompted to download the zip file through the download handler, which simply serves the zip file directly from blob store. So when describing any app, a great place to start is with data structures, and our app has two very straightforward data structures. The first is the overlay structure, and these are both the Go data structure definitions, which map directly to data store entity records. And at the top of the overlay struct represents any given map overlay. So when a user drags an overlay onto a map, along with the file upload, we create a overlay entity. And the first field in the overlay entity is the image field. And the image field is a blob key, a reference to that image in the blob store. The second one is a zip blob key, and that will be a reference to the zip file once it's been created. And then we have the pixel coordinates of the top left, top right, and bottom right of the overlay, which are used in computing the transformation. And finally, we have the number of tiles, the total number of tiles that will be generated, and we use that to figure out when we've finished generating all the tiles. And the other data structure that we have is the tile. And a tile has an image field, which is just a byte array, which will have the contents of our ping map tile image, and three other int64 fields, which are the x and y coordinates of the tile in pixel coordinates, and the zoom level at which this tile should be displayed. So now that I've given you that overview, I'm not going to walk through the entire application piece by piece, because it would take probably longer than we have now, and a lot of it is kind of minutiae that you can probably understand fairly easily on your own. So instead, we're going to talk about some of the design problems that we encountered when building the app and how we went about solving those problems. So the first problem was to make it reliable. It's easy to write a program that just runs from start to finish, and if everything goes well, then it's correct, right? But in the land of computers, things can and will go wrong all the time. And so we wanted to build this app so that if the slice process, for instance, failed at any point, it would just resume where it left off instead of having to start all over again. In some of the more higher resolution overlays, we're talking about thousands of tiles being generated, and it would be really inconvenient to have to just take the potluck that it's going to succeed to completion every time. So the solution to this was to use some of App Engine's APIs and build our app on top of those reliable fault-tolerant structures. And the first of these is the Task Queue API. And so Task Queues are a way of reliably scheduling and running work in a fault-tolerant way. And they come in two different varieties. Excuse me. The first are push queues, which are used to start workers. So when a task is entered into a push queue, it triggers some work. It calls an HTTP handler. And pull queues, which are consumed by workers. So workers actively lease tasks from pull queues, do the work, and when it's complete, they delete the task from the queue. In the overlay tiler app, we use push queues to start the slice and zip tasks. on backend instances. And we use pool queues to track the tiles that need to be processed. And so the slice task will lease those processes. The other piece of the puzzle are app engines backends. And so a backend is a special type of app instance that has greater memory and CPU allowances than a typical app instance. And they have longer request limits, so you can do much more longer running processes with backends. We set up a slicer backend that runs slice tasks. And the slice tasks are triggered by a push queue. And each slice task will lease tile tasks from the tile pool queue. And for each tile, it performs the transformation, renders the tile, stores it in the data store, and then removes the tile from that pool queue. So you can imagine that the tile queue is kind of asking for work, completing it, and then telling the task queue system that this work is done. And gradually, that tile queue is consumed until it's empty. And so in the diagram at the bottom, we see kind of that the slice push queue is triggering the task as a whole, and then the task is taking tiles out of the tile pool queue and turning them into rendered tiles. So if the slice task at any point fails, that's when the task queues really come into their own. If my slice task just dies in the middle, say it's rendered 2 tiles, but it leased 4 from the queue, the lease on those remaining 2 tiles will expire and go back into the tile pool queue. And meanwhile, another slice task has been created by the slice push queue, and those remaining 2 tiles can be leased, and the remaining work can be done without really skipping a beat. So that's how we made it more reliable. The second issue was making it faster. And so what we have here is an embarrassingly parallel problem, right? We have one source of data that's basically immutable, that is the tile overlay. And then we have many, many, many small jobs that need to be run over that piece of data. And so there's no reason that it should be done in serial, which is how we had it originally. So instead, we thought we would just run multiple tasks in parallel. And fortunately, the design that we have using task queues made it trivial to run multiple slice tasks across multiple backend instances. And to do this, all we needed to do was configure our backends to launch 4 instances of the slice backend instead of 1, and to process 4 slice tasks simultaneously instead of 1. And then in the in the process handler where we set up our slice tasks, we just add this little bit of code here. This is the only added code, is a for loop, and then we target each task to each one of the 4 backends, creating 4 tasks instead of 1. And that's it, and we got a 4 times speed up. And that was all we had to do, and it was quite nice. But I'm not that easily satisfied. The slice process itself, it requests tiles to be done, it performs the computation to generate and encode the tile, and then it stores it in the data store, and then it repeats that process again. But the actual, there's no reason we should have to wait for the transformation and the rendering to, there's no reason we should wait for the data store put to complete before moving on to process the next set of tiles. And so fortunately, Go's concurrency mechanisms make it really easy to do this. So this is a sort of very broad brushstrokes idea of how it worked without concurrency in a purely sequential way. So you lease the tasks, you render the tiles, store the tiles in the data store, and then delete the completed tasks from the queue. With concurrency, we still have our original lease tasks and render tiles in the task queue, but now we have this error channel for rallying Go routines, and then we just launch our storage and deletion parts of the process in another Go routine. And if you're interested in learning how this works and more about it, Rob Pike is giving a talk tomorrow morning, I think in this same room, and you should called Go Concurrency Patterns, and I highly recommend you attend it. It's a great talk. But the net effect of this is that in the case without concurrency, we had this sequential render input, render input, render input, and with concurrency, we were able to render tasks basically as fast as we could lease them from the queue, and put them all in the background simultaneously. And because the puts tended to take less time than the renders, it was always kind of in sync and caught up. And with that, we got another factor of 2. So with probably a net of about 15, 20 extra lines in our program, we got an 8 times speed up, which is nice. So the third design issue that we had was knowing when our tasks were complete. So when all the tiles have been generated, we need to know that they're all done and create the zip file. But when you've got multiple slice tasks all generating tiles simultaneously, just because one has finished processing tiles doesn't mean that another one isn't still going and still has more work to do. And it would be pretty bad if we started creating a zip file which didn't have all of the tiles in it, right? And another thing is we can't just kick off the creation of a zip file at the end of any one, because we might end up creating 4 zip files, and that's a waste of work. So to do this, we had to sort of manage state. And in App Engine, there are some bad places to keep state. One of those places is in app instances, which can just die. So there's no guarantee that they'll stick around. They're not unreliable, but you just can't rely on them. But memcache records may expire at any time. So because of the guarantees that memcache gives you, they guarantee consistency and accuracy, but they don't guarantee that they'll actually be there. And similarly, we can't just count the tiles in the client and expect the client to do the right thing, because clients can be broken or malicious or just disappear at any time. So the one good place to keep state in App Engine is in the data store. It's a consistent, structured, and a reliable place. And fortunately, we're already using it. So we just implement this algorithm to know when we're done. So at the end of each slice task, when a slice task has finished processing tiles and has no more work to do, it does a query to count the number of tiles that exist in the data store. And then it takes that count and compares it with the total number of tiles that it's expecting. So we had a field in the overlay that was recorded with the number of total tiles. And if the total number of tiles exist in the data store, or if there aren't enough tiles in the data store, we know that it's time to keep slicing. So we go back to the start and try and find more work to do. Otherwise, we check the zip running value in the overlay record. Actually, sorry, I omitted that from the slide. There's actually a Boolean field in our overlay struct that indicates whether we've created a zip task or not. And if a zip task is already running, then we're good to exit and shut down the slice task. But if neither of these two conditions have been fulfilled, it means that all the tiles have been generated. It's time to start zipping up the tiles. And so we add a task to the zip push queue, and then we set the zip running flag to true in the overlay record and put it back into the data store. So that is fairly straightforward, but it's racy. So if we try to actually run this, if there's a chance that both two slice tasks could compare the number of tiles and not see that there's a zip file running, but then create 2 zip files simultaneously. And so the solution to this is to just run it inside a data store transaction. And with the Go runtime, that's as simple as creating a function closure which encloses all of these operations, and then run them with the run-in transaction function. And this even applies to adding the task to the task queue. So task queues are incorporated in data store transactions, and that's a really nice mechanism. And so our fourth and final problem is communicating with the user. So after the user's clicked the process button and all these slice tasks have been fired off and the zip task has been fired off, there's no back channel to the user. The backends are running these instances, and the user has no direct communication with the backend. And not only do we need to tell them when it's done, we also need to tell them, like, as it's going, what the state of the program is, so that they have some indication that it's actually doing something and not just stalling. So the means for doing this with App Engine is the channel API. And the App Engine channel API just provides a push channel from App Engine instances to the user's browser. And the mechanism for doing this is really simple. There's just two functions on the server side. There's the create function and the send function. And so the create function just takes an ID of your choosing, which uniquely identifies the channel, and then returns a token, which you pass to the client. And the client uses some JavaScript to create that channel using the token. And then sending a message, you just provide the client ID and the message that you want to send, and it's any textual string that you can send to the client. And on the client side, there's some JavaScript. You just create a new channel object and open it, which returns a socket. And then the socket has an onMessage handler, which, when called, will pass a message object. And so this code will just log the message to the console every time a message comes through. And there are also some other handlers to detect the opening of the channel, the closing of it, and errors and so on. So in our app, the Go's support for JSON encoding of native data types makes it really clean and nice. We just define a message struct, which is the structure of the message we want to send to the client. And then we use this send JSON function to send a JSON encoded version of the Go data structure to the client. Now, our message struct contains 4 fields. The first is the total number of tiles in the overlay. And the second is a list of IDs of tiles that have been processed. So in this second code snippet here, this is what we do after processing a bunch of tiles. We send a message to the client that contains the total number of tiles and the IDs of those tiles. And then the client adds them to a list of tiles that it's keeping track of. The other 2 fields, tiles done and zip done, are just Boolean flags to indicate what other stages of the process. So once all of the tiles have been computed and the slice task has detected this, it sends this message just with setting the tiles done equals true with send JSON. And then the final message that the client will receive is the zip done message. So we just send a message with zip done set to true. And on the client side, we set up a channel by opening the socket and register a message handler. And in the message handler, we JSON decode that message and check the fields of the message to see what kind of message it is. So if zip done is set to true, we redirect the user's browser to the zip file. If tiles done is set to true, we display a creating zip archive message. And if IDs is set, it means that we're getting progress information about the tiles that have been computed. And so we add those IDs to an object named tiles. And this object just collects, it's essentially a set of all of those tile IDs. And this means if we receive IDs more than once because a task has failed in some way, it means that we're not counting tiles more than once and we won't end up showing 110% tiles being computed, say if we received messages more than once. So it's just a form of deduplication, essentially. And so we display a percentage of the number of tiles that have been computed in that case. So now we'll just demonstrate a, do you want to operate this?
So hopefully the demo gods will shine upon us.
Well, they shone upon Sergey yesterday, so this is a much smaller ask.
I'm far less worried than he was yesterday as well.
Yeah. So now we're going to try a bit of a bigger image, which is Götaland, off the coast of Sweden, is it? And this is from USGS's, what's the project called?
I think it's called World is Art. So they've got some really beautiful satellite imagery. This is one of my favorite. It's called Van Gogh from Space. So it's a photo of this island, and it's just some really amazing imagery. So if I go ahead and search for Gotland, not Scotland, and drag and drop this image, you can actually see this progress bar moving. So I was able to manipulate the image. I didn't, but it was just uploading in the background. And I can just position it. Actually, it's probably better to go into satellite mode for this one and knock back the opacity. Maybe if I zoom out. and just get it. I'm not going to spend too long doing this. Apparently Andrew's much better at this than me.
Just do it.
That looks good. Okay, let's hit process. And so this is quite a large overlay, actually.
So now you can see it's processing tiles, and if we look at the instances, you can see there are 4 slice instances that have been spun up. And if we look at the task queues, it's refreshing now. At the bottom, you can see that there are 1,100 tasks in the queue, and 180 have been leased in the last minute. And so if we keep refreshing while that's going, you see we're up to 17% now. More tasks have continued to be leased, so they're being consumed from the queue as it churns through, and we have the 4 instances still running. And you can see their CPU time. They're actually not working that hard. It must be data store dominated. And then if I refresh the logs, we can actually see the active backend requests and log messages being pushed through from the backends in sort of semi-real time. And so each one of these 10 tiles messages means that 10 tiles have been computed. And so we can see it's nearing completion. And I should also note that you can see in the slice queue, there are 4 tasks in the queue, and there are 4 running simultaneously. So that's our 4 slices going. And you see there's actually been like 1 or 2 errors there, and they've just been gracefully restarted and picked up again. And so now the zip archive is being created on the back end, and it should be served to us, and then appear in our downloads, which is this one. Is that it? Let's check the tiles. Nope, that's not the one. It's this one. So now if I open the index.html, I'll see the overlay on the island. And so if I zoom in, I can start to see the greater detail. Cool. So I just wanted to talk a little bit about the reasons why we chose Go to do this, as opposed to the Python or Java runtimes on App Engine. So first of all, Go has great standard packages, which we took full advantage of in this app. Next is there are great external package support, driven by a really vibrant open source community. And we used a graphics Go package just to perform the affine transformations. And that package is actually built atop the built-in image packages. And there's this great site, Go Package Doc, which you can visit to get a list of the thousands of open source packages that are available, of varying degrees of quality, of course. And the main reason for choosing Go on App Engine for this task is that it's the only App Engine runtime that lets you run user-provided code in native machine code. So you get the full performance of the machine that it's running on. It's not running in a virtual machine. It's not virtualized. It's just real code running on real cores. And so you can really crunch some serious numbers with Go on App Engine. And finally, I think Go is just a great language all around. It's simple in its design. The language and the libraries are consistent and easy to use when combined. And it makes for a very comprehensible and cohesive programming experience. And also, Go provides some great concurrency primitives. And as we saw very briefly, I was able to get a factor of 2 performance increase in my App Engine app just by introducing a small amount of concurrency in one of its core components. So the code for this app is available in a Google Code project, overlay-Tyler. And you may want to wait a few minutes because we're going to push an update just after this talk. If you want to learn more about the Maps API, visit developers.google.com/maps. And similarly, to learn more about App Engine, visit the same domain /App Engine. And to learn about Go, visit golang.org, which contains a wealth of documentation, as well as an interactive online tutorial and some other fun stuff. So thanks everyone for coming along today on behalf of Chris and I. If you have any questions, we'll be happy to answer them now, but thank you. Just step up to the mic if you want to ask anything. Or not. Or you can just all go to the next thing. No? Cool. Hey.
Yeah, just curious about how much compute power you used on that exercise, and in terms of translating it to
costs?
Yeah, cost, or running it on your own server.
Sure. So my understanding is that these app instances cost, and don't quote me, but it's somewhere in the realm of 10, 15 cents an hour, because they're the highest ones that we have. But I'm not 100% sure on the cost.
Can we look at the cost in the logs?
We probably can, but I don't want to, for reasons you know about. And so not because it's high, but because it shows some internal stuff, because we're logged in as our google.com addresses. But you notice that there are 4 instances running now, and because they're dynamic instances, they'll actually only stick around for like 5, 10 minutes max, and so you actually only pay for a fraction of that hour for a bursty kind of job like this. And so backends can either be configured to run like continuously, in which case you just pay like a constant rate, or they can be, if they're dynamic, they'll just spin up when they're needed, and then they'll spin down. And you can actually control when backends are started and stopped programmatically as well, using specially formed HTTP requests. Yeah.
Can C-Go work with this on App Engine?
Sorry, can C-Go? So the question was, does C-Go work with App Engine? And C-Go is a function call interface for calling into C code from Go code. And the answer is no. The Go App Engine runtime only supports Go code, because the memory safety that we get from Go is what allows us to run your code safely on our servers. Otherwise, we wouldn't have that security. C is a fundamentally unsafe language. Thanks.
I'm just curious about what kind of errors do you get, for example, for this kind of task most times? Because it doesn't seem to be that, seems to be a bit frequently, and what kind of errors?
So typically the kind of errors that we see are, in some cases, out-of-memory errors. So if you have like a particularly large overlay, and then you slice a large number of tiles, if in some cases the garbage collector hasn't caught up, your app instance could be killed because it's run out of memory. And we haven't seen a lot of that. We've seen a few instances with some really big overlays. Other things that can happen are, because App Engine is distributed across multiple data centers, you can sometimes end up with like hiccups in the network where a particular data store request, be it a put or a get, will be hung for a short amount, for longer than a particular request deadline, and then your instance will be killed. It's basically just because you're working on a large distributed system, you get a lot of, we guarantee consistency, but we don't guarantee that, I don't know how to phrase it properly. I probably should know. But yeah, it's basically you get, in any system you get errors that you don't expect, right? So you have to design it assuming that any particular part of it will fail. Yeah.
Hi, I'm actually the developer of MapTiler you mentioned earlier, and I'd like to ask you, what's the intended use of this system? Is it something public, or is it internal for Google? And if it's public, what's the biggest size of image that you are able to process, or what is it that you have tried already?
Mm-hmm. Sure. So yeah, we definitely designed it to be public. So the source code is completely available, and
but as a service, we didn't design it to be launched as like a Google service or a product. It's really just a pedagogical exercise in learning about the Maps API and learning about Go and App Engine.
Yeah, so if I wanted to, I could run it on my own instance of App Engine, but
Absolutely.
It's not a Google service. Okay, I understand.
Yeah. And we do have, we were running it on a public instance now, but for the purposes of our demo, it's not available to you all in case, adds a level of unpredictability. But we do intend to open that up for people to use, but anyone's free to deploy it wherever they want as well.
And the question about the image size, what is some upper limit that you have tried, or something like that?
So,
the biggest images we've put in have been between like 15, 20 megabytes as a JPEG. And so image size that's approaching about 10,000 pixels on a side.
Yep.
Between, I think, 7,000 or 8,000 pixels maybe.
Mm-hmm. So it's really bounded by the size of the instances that we're running on. So as Andrew mentioned, we were running into some out-of-memory issues on larger overlays.
But nothing that we weren't able to solve in the end.
Yeah.
So I think ultimately the upper bound of the image you can load is one that you could decode within the memory limits of a large App Engine instance. And I think the limit is 1 gig. You have to check the website to be sure. Yep.
What is the workflow like of developing and debugging an app that is written in Go and runs on App Engine?
Great. So the Go App Engine SDK is built on top of the Python SDK. So it comes with the same development app server that you can use to run Python apps locally. And so when you work on your Go app, you launch the development app server, and it will automatically compile your Go app and run it. And then you can just access it via localhost in a browser. If you make changes to your Go source code, the code is recompiled, and so you get the same kind of edit, refresh, test cycle that you get with scripted web apps. And because Go code tends to compile usually in sub-second times, usually sub-100 milliseconds in some cases, you don't really notice the difference between that and working on Python apps. And in deployment, it's all feels exactly the same as the other Python platforms. It uses the Python app CFG tool for deployment. Oh, and one thing that's probably worth mentioning is that if you have existing Python or Java App Engine apps, you can deploy backends that run Go code. So if you already have some user interface, you can write your heavy lifting code in Go and just have a hybrid setup like that, and there's no issues there. Cool. If there are no other questions, thanks again, everyone, for coming along, and I'll see you at the rest of the conference.